So whenever I talk about a new functional group, I'll always make reference specifically to boiling point, solubility, and if it applies pH characteristics. Boiling point is the temperature at which molecules intermolecular forces are overcome and the molecules separate into a gas form. As an example, let's go ahead and go up here. In this example at the very top, I have a variety of hexane molecules found in this box right here. And basically, we assume that temperature is movement. So the higher the temperature, then the more the movement we have present. So for example, highlighting this heptane molecule right here, as we increase the temperature, we'll start to see it rock and shiver. So it'll go back and forth, or it may start rotating back and forth, and all of these molecules are going to do exactly that. So you'll see a molecule over here, and it will start to shiver, and then it will start to rotate. As we increase in temperature from a solid to a liquid, these molecules will start to move around each other. Heptane at room temperature tends to be a liquid, so you'll start to see it move around, and the various molecules will, if I can get a hold of one, come on, will start to, ooh, that's weird. The various molecules will start to move around each other. Now, when I start to get to a gas, go from a liquid to a gas, that temperature, called the boiling point, that's when all of the molecules, their intermolecular forces are overcome due to the constant movement, and they fly off into oblivion. Okay. Now, in general, the higher the boiling point, then the more powerful the intermolecular forces to get to that higher boiling point required. So molecules which have ionic forces, for example, have a much higher boiling point than molecules such as these right here, which have London forces. The next one is solubility. Solubility. It's how well the molecules dissolve or mix perfectly with another substance. Again, they're tied into intermolecular forces, and the intermolecular forces, whether they're overall polar or nonpolar. The overall polar or nonpolar we refer to as the polarity. So going back to this example a little bit lower, here I've temporarily mixed together water and heptane, and what I'm going to do is, it turns out that polar substances are soluble in polar substances. Nonpolar substances are not soluble in polar substances. So we have to first determine, looking at its intermolecular force, is it polar or nonpolar, and therefore is it overall soluble or non-soluble. So in this case, water is polar, heptane is nonpolar, so you'll see over time that they'll start to separate. The denser one will go ahead and be on the bottom, and in this case, if this were a beaker, then you would see them separate, and the heptane would be on top, the water would be on bottom. The last characteristic is pH, and this some of the molecules, they're similar to a weak acid where they give off hydrogens, or maybe they may receive hydrogens. So those are the acid-base characteristics, and those we really get into in future chapters. But for right now, I'm going to focus heavily and explain more thoroughly boiling point and solubility. To do this, though, we need a background on intermolecular forces. What intermolecular forces are present? This gives us the insight into boiling point and solubility. So going to slide 2. Here are the 4 general intermolecular forces you have to learn for this class. Yes, there are other ones, but those are the 4 that you have to learn for this class. In general, the first 3 can be classified as being polar, with the most polar being ionic forces, the second most polar being hydrogen bonds, H bonds for short, the third most polar being dipole forces, and the fourth being London forces. In general, I will try to make things as black and white as possible. So these top 3 forces oftentimes can be classified as general polar, whereas the bottom force can be classified as generally nonpolar. In reality, we have a combination of competing intermolecular forces. So oftentimes you'll hear me say the words, what is the dominant intermolecular force for a particular molecule? So for example, if I take a look at this molecule that I'm highlighting, this is a hydrocarbon derivative with what's called a amine group attached. Notice it's part hydrocarbon and then part amine functional group. It turns out that there is some London force that's happening on this left-hand side. However, the dominant intermolecular force in this molecule is going to be due to this amine group, which contributes the hydrogen bonding intermolecular force. And this hydrogen bonding intermolecular force is basically going to overshadow the weaker London force. So yes, it is possible to have multiple intermolecular forces, and that's why I tend to say the words the dominant intermolecular force. So moving on. Moving back, in general, we get the term polar based on the fact that we have a pole. On one side of the pole, it's going to be a positive side. On one side of the pole, it's going to be negative. And the more polar the molecule, the stronger the opposite charge. Consequently, the stronger the opposite charge attraction. So a little insight into polar terminology, though I'm not going to test you on that terminology. The strongest polar group is ionic forces. If you took 101, salt was the best example. Here is a picture of a salt molecule with the positive being the sodium portion of the salt, and then the negative being the chloride portion of the salt. In organic chemistry, we have hydrocarbon derivatives where we have something similar where there will be a metal attached, and that will be the positive portion, and then you will have the negative nonmetal. And again, opposite charges attract. In this case, this is sodium benzoate, and sodium benzoate is one of the most popular preservatives found in drinks. It actually works because it actually works by newly forming bacteria. It will actually go inside the bacteria and basically prevent it from reproducing itself. So that's how sodium benzoate works. I'm going to go ahead and skip hydrogen bonding so we can go straight to dipole-dipole. These are molecules where they're all nonmetals, and I want to focus on this example on the left right here. This is a polar molecule. And then basically what happens is we have opposite charges that occur, and in this case chlorine is going to be a partial negative and hydrogen is going to be a partial positive. This occurs because of electronegativity. When we have a bond where there are two different atoms, one atom will be a little bit more greedy with the electrons between the bond than the other. We call this electronegativity. So in this case, because chlorine is more electronegative than hydrogen, then the electrons are going to be pulled to the right. We represent this by writing a dipole symbol, which I'm going to highlight right now. And then it turns out that here we have a positive and negative, and then the intermolecular force is due to opposite charge attraction, where you have another molecule with a dipole, hence dipole-dipole interaction. In the next slide, we see an example of this. Here is dimethyl ether. I'm going to go ahead and use my blue pen, or use my blue marker. Here's dimethyl ether, and it has a dipole that's present. And with a positive and negative side, it's going to go ahead, the negative portion is going to be attracted to the positive portion of another dipole of a nearby molecule. Hence the term dipole-dipole forces. In general, when you're figuring out if it's dipole-dipole or not, let's go back to the previous slide. We need to figure out if there is a net dipole. Another term for this is if there's an overall dipole. Another term for this is if there's a molecular dipole. So net dipole, overall dipole, molecular dipole, these are all the same terms. And this is what you need to figure out if there is a overall dipole present and whether it be classified as dipole-dipole. So in this example right here, I have ammonia gas. And what I'm going to go ahead and do is I'm going to show the direction of the individual dipoles. In this case, nitrogen's more electronegative than hydrogen. So here are the individual dipoles. Now, these two dipoles, they cancel each other out, but there is one leftover dipole going up. So therefore, there is a overall dipole. To the right, it shows the individual dipoles, since technically it's trigonal pyramidal. And then here is the overall dipole direction. Hence, when we have two of these molecules together, we say that they're attracted to each other, opposite charges attract due to dipole-dipole interaction. And we're referring to the fact that it's overall dipole interaction. Again, same example going back to this one. We have two dipoles. This is a bent structure. So there is a overall, let me go ahead and erase all the ink. There is a overall dipole-dipole. For that molecule, there's an overall dipole-dipole for that molecule. Opposite charges attract, and therefore this could be considered a dipole-dipole interaction. Hydrogen bonding is a very, very special form of super powerful dipole-dipole. It's so powerful that it gets its own name, in this case, hydrogen bonding or H-bond. So we start off with a molecule that already has a dipole, and then if it matches the following additional criteria, it's considered hydrogen bonding. So in this case, if there are hydrogen that are attached and electron pairs that are found on either a nitrogen, oxygen, or fluorine, then it's automatically hydrogen bonding. So we can have hydrogen bonding occurring between pure substances or a mixture of substances. In these examples over here, we have hydrogen fluoride, and hydrogen fluoride has a hydrogen that's attached to a fluorine. And notice on hydrogen fluoride you have lone pairs that are on hydrogen fluoride. When we mix it together with water, water has lone pairs attached to oxygen and hydrogen attached to oxygen. Hence, this would be considered hydrogen bonding. So you can go through these examples right here. Here we have methanol. Notice there's a lone pair which is implied, and then it has hydrogen that's attached. Hence, this is hydrogen bonding. This molecule here, again, lone pair and hydrogens that are attached. notice the hydrogens have to be directly attached to a nitrogen, oxygen, or fluorine. Also notice, this is why I've strongly encouraged you to put lone pairs on your nitrogen, oxygen, or fluorines, and this will help remind you if it is in fact hydrogen bonding or not. Moving on, we have molecules which are considered nonpolar, hence their dominant intermolecular force is always going to be London forces. So in this case right here, chlorine gas, electronegativity wise, there is no overall dipole. Consequently, it's considered a London force. Here's a pretty cool molecule right here. This is a hydrocarbon derivative. However, each one of these intermolecular forces, if we looked at the individual dipoles, they all end up canceling each other out. Oops. So they all end up canceling each other out. So let me go ahead and go to a blue pen. So these two cancel each other out, these two cancel each other out. So there is no overall dipole. Hence, it's automatically London forces. So, as a result, here we have a dilemma. All intermolecular forces for this class are due to opposite charge attraction. However, what do we do with dilemmas where the dipoles all cancel out? Well, we go ahead and we make up a temporary dipole. This temporary dipole we call London forces or dispersion forces. And this is how it works. We start off with two molecules, and one molecule, all of a sudden, as I highlight it here, we're going to have energy from the nearby environment. And it's basically going to cause electrons to rock one side or the other. Consequently, it generates a temporary dipole. And I draw the dipole symbol here. When this molecule is near a nearby other molecule, it induces another dipole in the other molecule. Hence, we now have a temporary dipole-dipole interaction. It's a lame reason, but this is what scientists have come up with, and so we're just going to go ahead and run with it. Here is a nice summary of intermolecular forces, which you absolutely need to know.